The second requirement of logistic regression is that we have no complete separation. Complete separation occurs when one or more variables classifies the observations into successes and failures perfectly. And I don't want that. Why don't I want that? Why wouldn't I want perfect classification of successes and failures? I definitely want to be able to predict them with extreme accuracy. So perfect prediction seems like it would be a good thing. The problem is, if we can do this prediction perfectly with just one variable, then we don't need a model. We just need a rule. Remember, throughout the class, I've told you that we shouldn't be able to do this perfectly. A model is not intended to perfectly predict what is coming. If we could do that, then we would do that. We wouldn't create a model. So if we can perfectly classify successes and failures without a model, then we would want to stick to the easiest possible method. So we should just use a rule instead. And I think you'll see what I mean shortly. So the example is, if age greater than or equal to 21, then a person can choose whether they want to drink or not. If the age of a person is less than 21, then there's no choice. That person is not able to drink. So why would I use a logistic regression model to predict if a person can choose whether to drink? I don't need one. I just need to know their age. So I could just check their driver's license and perfectly predict every time whether a person has that choice. So why would I create some complicated model to do it? So that's all this is saying. If you can perfectly classify with just knowing one variable, then you don't need to have a very complex model. Just use a rule. So don't predict anything complicated, anything simple with a logistic regression model. Logistic regression is a complex method that's intended to do the best job we can, but not to be perfect. So let's think about this from a technical perspective. Why is this the case? Why can't we use a logistic regression if we'd have perfect prediction? So look at this chart. This is a chart that will help us translate from K into P. And K is the log odds ratio. P is the probability of success. So we've seen the simpler version of this in the video I made called Interpretation Rule of Thumb. And we saw that as K gets more negative, P gets smaller. And as K gets more positive, P gets bigger. But I left out this complicated thing in the middle here, this curvature. So just to point out again, K is the log odds ratio, and P is the predicted probability of success based on that log odds ratio. From this model, we have an easy time telling where the successes are, and we have an easy time telling where the failures are. But there's this mysterious part in the middle that is harder to tell. The probability of success is just less clear. It's around 0.5 or 0.4 or 0.6, and it's more ambiguity. So we're not extremely confident of our predictions. And if we don't have these ambiguous cases where we're not quite sure, then we can't fully define this model. This is a logistic regression curve, and we have selected to use this curve. But if we only have the zeros and ones and there's nothing ambiguous in the middle, then R is going to give us an error because it can't define the shape of the curve. The only reason this is a problem is because we chose to use this curve, so we have to be able to define it. So that's the technical reason why we can't have perfect classification using our variables. So how do we test whether we have complete separation? Let's get back to the practical aspect of this requirement. So we're going to plot the predictor versus the outcome. So in our example, we'll use donation on the vertical axis, that's the outcome, and we'll have age, our first predictor, on the horizontal axis. And the ages for this data range from about 20 to about 70. And what you can see in this picture is that donation binary is zeros and ones, and that lots of different ages donated and lots of different ages did not. So the question for how to tell if we have no complete separation is, can we separate all the zeros and ones with a single vertical line? So can I draw a vertical line such that, so here's an example line. Can I draw a vertical line such that everything to the left is a 0 or a 1 and everything to the right is the opposite? While looking at this vertical line, we have ones here and we have zeros here, and we have ones here and we have zeros here. So we have not separated. Now, if I were to move the line to the left, will I have done a better job? No. If I move the line to the right, will I have done a better job? No. Now, when I move all the way over here, let's say I draw my vertical line here, then I have just ones to the right of it. So everyone over the age of 62 did donate. But then to the left, I have people that did and people that didn't. So I still haven't been able to tell if I have complete separation. Now, just for example, let's draw another one down here, age and donations. What if I had all zeros here and all ones here? And let's say this age was about 50. Then I could indeed draw a vertical line that would separate everyone over 50 who donated and everyone under 50 who did not. That would be complete separation. And then I could use the age 50 to say, we'll just make a rule instead. Everyone over 50, I'm going to predict that they do donate, and everyone under 50, I'm going to predict that they don't. And I don't need a logistic regression model to do this. But in this case, our data shows more ambiguity. So we can proceed. We do not have complete separation in our model. If you can separate, then you have complete separation, and you should simplify the model into a rule. Always use the simplest model you possibly can, and in that situation, where 50 was a divider into successes and failures, we can just use the rule age greater than 50, yes, age less than 50, no.